Hello, class. Today we are covering 3.4 real zeros. Real zeros as opposed to imaginary or rational zeros. So real zeros of polynomials. Okay. So in the last section, we learned about synthetic division. So we're going to be using that here in this section. All right, so 3.4. Real zeros of polynomials. Okay. And we're going to be looking back again at graphing higher degree polynomials, but this time they aren't so easy to find the zeros at the beginning because they're not factorable, so we need to use our synthetic division to find those zeros. And remember, zeros are the same as the x-intercepts. Okay, so we are going to start with the rational zero theorem. So actually, I think I misspoke earlier. I said real zeros of polynomials as opposed to imaginary or rational. Rational numbers are real. So real zeros as opposed to imaginary. Okay. All right. So we have the rational zero theorem, which states that if p of x, this is our polynomial, has integer coefficients, then every rational zero has the form So remember, a rational number is a real number that can be written as a fraction, right? As a fraction, a ratio, hence rational keyword there, root word there, ratio. So it has the form P over Q. There's your ratio, where P is a factor of the constant okay? And Q is a factor of the leading coefficient. Okay, so what's going to be happening here? So zeros are the same as solutions, which are the same as the x-intercepts, right? And so we looked at how to use synthetic division to find the zeros, right? If we ended up with a zero remainder, then we found a solution, or we found an x-intercept, okay? So what happens here is when your initial polynomial that you're trying to solve or graph isn't initially factorable, then we have to go through synthetic division to find those initial zeros. Okay, now the question is, where do we start? Do we just pick random numbers? You know, those are a lot of numbers, right, to choose from, and to decide, okay, well, let me just start with 17. Okay, so we're not going to be just picking these numbers randomly to test it out using synthetic division. Okay, so we use this theorem here that's telling us, well, if it's a zero, a rational zero, it's going to have this form, P over Q, where that top number is going to be a factor of the constant, and that bottom number is going to be a factor of the leading coefficient. So that's where you're going to start. You're going to make your list, okay? You're going to make your list here. And if it doesn't have that form, P over Q, you don't have to try that number to see if it's a zero, okay, a rational zero, okay? All right, so for example, suppose that you have this polynomial. P of x equals negative 2x to the fourth plus 13x cubed minus 21x squared plus 2x plus 8. Okay, so we have this polynomial here, clearly not easily factorable when we look at this. Okay, so we're going to be using that rational zero theorem to at least narrow down our choices for these rational zeros. Okay, so it says that it has to have that form P over Q, where that top number P is a factor of the constant. So here's my constant right here. Okay. So then my possible p-values are going to be, well, and I'm going to use the positives and the negatives because, of course, I can do 1 times 8 or negative 1 times negative 8, right? So both positive 1 and negative 1 are factors. Positive 8 and negative 8 are factors, okay? So plus or minus 1, plus or minus 2, plus minus 4, and plus minus 8. Okay, so those are going to be my possible numerators. Okay, and that says that Q, the denominator, is going to be a factor of the leading coefficient. Okay, so right here, this is my leading coefficient here. So these are going to be my choices for Q. So it's going to be plus or minus 1, plus or minus 2. Okay, so then now I can make my list of possible rational zeros by putting all the different combinations of P over Q. Okay, so we're going to do the plus minus P over Q. Okay. All right, so I don't want to have to write plus minus in front of every single number. So let's just, let's do this. And we'll know that, and then we'll know that we're testing, we can test the positive and the negative. Okay. All right. So P, I have 1. So I can do 1 over here, 1 over 1 over here. Okay. So 1 over 1, which is just 1, right? I can do 2 over 1. Okay. I can do 4 over 1. And I can do 8 over 1. Okay. And now I'm going to use the 2 over here where the Q is. I'm going to use 2 for the denominator. So I'm going to do 1 over 2. And I'm going to do this one next, 2 over 2. And I'm going to do, but you know what? 2 over 2 is the same as 1 over 1. So I'm not going to use that. Okay. We already have it here. And then I'll do 4 over 2. Oh, but 4 over 2 is the same as 2. So I won't use that. We already have it over here. Okay. And then I have 8 over 2. Well, that's the same as 4, and we have 4 over here. So I don't need to write it again. Okay. So then right here, So if you have a rational zero here, then that means that it's going to be either positive or negative 1, positive or negative 2, positive or negative 4, or positive negative 8, or positive negative 1/2. Okay? So you first need to make your list, and then you can use your synthetic division and test each one until you come up with a zero remainder. Yes, it's going to take a lot of work. So you can expect to get not a whole lot of problems, okay, from this section, because yes, they do take a long time, especially if you're very unlucky when you guess your first try, okay? All right, so let's try another one. Why don't you go ahead and try this? List the possible rational zeros. Okay. If you feel like you understood that last one, go ahead and hit the pause button when I put down the polynomial and give it a try. If you feel like you can use another example, then keep playing. Okay, suppose that you have this polynomial, 4x to the 5th minus 8x to the 4th. And by the way, yes, these do have to be in descending order. I'm not sure if all the problems will be in order for you in your homework. It's kind of cruel not to put them in order because there's so many little details here. Okay. All right, so here's your P. So my different P values are going to be plus or minus 1, plus minus 2. Okay. Here's your Q value. So I need the factors of 4. So I need plus minus 1, plus minus 2, plus minus 4. Okay. So my possible PQ. Okay, let's see. I always like to start with all of these guys over the first one, and then all of the P's again over the 2, and then all of the P's again over the 4. Try to come up with some sort of systematic way of keeping track of all of your possible P over Q's. All right, so again, we're going to take all the positive and negatives, and we're going to do 1 over 1, 2 over 1, and then 1 over 2, and 2 over 2. Okay, but 2 over 2 is the same as 1, so let's cross that out. And then 1 over 4, and 2 over 4. But 2 over the 4 is the same as 1/2, so we don't need that one either. Okay, so this is your list. It's going to be 1. You can reduce these here. It's going to be 1, 2, 1/2, 1/4. And of course, positive, negative. Positive, negative, all of these. Positive and negative 1. You can try with synthetic division. Positive, negative 2. You can try with synthetic division. Positive 1/2, negative 1/2. You can try. Positive 1/4, negative 1/4. You can try. Okay? All right, so let's actually start finding the rational zeros. Okay, so determine rational zeros. Okay, so you definitely want to start by listing your possible P over Q zeros. Okay, once you have your list, then you're going to test each one. So yeah, it'll be a pain if you have a very long list. Okay, you kind of keep your fingers crossed and hope that the very first one you choose to test turns out to be a 0. Okay, all right, so you test each one using synthetic division. Okay, and again, you're looking for 0 remainders. Okay, because if you have a 0 remainder, then we said last time that it's a 0, right? And if it's a 0, then it's an intercept. Okay. So when you find these zeros, try to see if you finally end up with a degree 2 and try to factor it. Okay. All right, so let's go ahead and put our list together with synthetic division that we learned last time. Find the rational zeros. So here's your polynomial. P of x equals 2x cubed plus x squared minus 13x plus 6. Okay, so clearly this polynomial is not factorable. Okay, so we wouldn't be able to graph this right off the bat because we can't find the zeros. Okay, so we're going to use the list. All right, so over here, our possible p's are plus minus 1, 2, 3, and 6. All the factors of 6. Okay. And then over here, our possible denominators, our q values, are plus minus 1 and plus minus 2. Okay. So all the different combinations of a p over a q. So I'm going to start with the p value 1. Okay. And of course, we're testing all the positives and negatives on our list. Okay. So I'm going to start with that p value 1 and that q value 1. So I'm going to get 1 over 1. I'm going to get 2 over 1. I'm going to get 3 over 1. And I'm going to get 6 over 1. Okay, moving on to the next denominator, which is going to be this q value over here, 2. And I'll do 1 over 2, 2 over 2. But that's the same as 1, so we don't need that one. 3 over 2. And 6 over 2. But 6 over 2 is the same as 3, so we don't need that. Because again, it shows up over here. Okay. All right, so these are the ones that we want to try. So we want to try all the positives and negatives of this list. 1, 2, 3, 6, 1/2, and 3/2. Okay? All right, so now we begin. Okay, so there's my polynomial right up there. So I'm going to go ahead and put just the coefficients. So 3, 2, 1, 0. Nothing is missing. It's in descending order. So we're going to get 2, 1, -13, and 6. Okay. All right. So now from here, you can choose, you can start however you want. I always like to start with the smaller numbers and just kind of go in order. So I'm going to try to see if x equals, I like to start with 1, and then -1, and then 2, and then -2, 3, and then -3, 6, -6, and then I just start on my fractions. Okay. All right, so I'm going to start with 1. So, and we're hoping for a 0 remainder. All right, so we bring down this 2. 2 times 1 is 2. Combine. 3 times 1 is 3. -13 and 3 is -10. -10 times 1 is -10. And here I don't get a 0, so x equals 1 is not a solution. It's not an x-intercept. Okay, so let's try again. Okay, so let's try -1. Fingers crossed. 2, 1, -13, 6. Okay, bring down the 2. 2 times -1 is -2. Lots of room for error here, so just kind of be patient. -2 plus 1 is -1. -1 times -1, +1. -13 and 1 is -12. +12, and we get 18. Again, no 0 remainder. We got an 18 for the remainder. Okay, let's try 2. Okay, so it was 2, 1, -13, and 6. Before I go on, let me make sure I copied the problem right. Is it +2, 1, -13, 6? Yes, it is. Okay. 2 times 2 is 4. 4 plus 1 is 5. 5 times 2 is 10. -13 plus 10 is -3. Uh-oh, look at here. 2 times -3 is -6, and we do get 0 for our remainder. So happy face here inside the 0. Okay. All right, so right here. So this is one of our zeros so far. And if you remember from the last section, this is 1 degree less. So we started off with a degree 3, I believe. Let's see. Trying to scroll up here. It is a degree 3, right? Degree 3 right there. So now this polynomial is a 1 degree less. So this is a degree 2. So this is 2x squared plus 5x minus 3. Okay, so we can try to factor that. Okay, that's why we like it when it's down to a degree 2. Now, let's say that the original polynomial was a degree 4, and then we found the first 0, right? Then this polynomial in here would have been a degree 3. So what you could do is continue working off of the degree 3 polynomial and use synthetic division on the degree 3 polynomial, on this one over here. Okay, like we can do that now, even now, you know. Oh, and one thing you also want to do is if you do get a 0, try it again, because it could be a double 0. Could be double 0. So it could be a 0 again. Okay. All right. So I'm going to go ahead and see if this factors. If it doesn't factor, then I can use quadratic formula. Okay, 2x times x, positive and a negative. Let's see. I'm going to try negative there and a positive here. 3 and 1. 3 here, 1 here. 6 on the, this gives me 6. This gives me negative 1. 6 minus 1 is 5. So this is correct. So now I can solve this. 2x minus 1 equals 0. So x equals 1/2. So there's my second 0. And then x plus 3 equals 0. So x equals negative 3. And there is my third 0. Degree 3. And I have 1, 2, 3 zeros. Okay. 1 for each degree. Okay. So there's a theorem that says that if it's a degree n, then you will have n zeros. Do they all have to be different? No. Okay, so I could have had one of these repeat again. Okay, but you will have n zeros, not necessarily distinct. Okay, so let's have a look at another example. So here, let's take a look at the language here. So if you notice here, it says find the rational zeros. So rational being written, a ratio of 2 integers. Okay, so these numbers here are rational numbers. Our first 0, x equals 2, x equals 1/2, x equals negative 3. Okay, so let's say it wasn't factorable and you had to use the quadratic formula. And if it's not factorable, then you use quadratic formula and you end up with like a square root in your answer. Okay, that's not a rational answer. Okay, it's irrational. Okay, so you would not include it here if it says to find the rational zeros. Okay, if it says to find all the real zeros, then yes, you can include it. If it says to find all the zeros, then you include all the ones with radicals, all the rational ones, and also the imaginary ones. But we haven't covered imaginary numbers yet, but I'm sure you know about them. Okay, so just pay attention to the words. So that one said find the rational zeros. So no radicals, definitely no imaginary. So let's take a look at this one here. And this one will say find the real zeros. Find the real zeros of this polynomial. 3x cubed minus 5x squared minus 8x minus 2. Okay, so here my p-values are going to be plus minus 1, plus minus 2. Over here, my q-values are going to be plus minus 1, plus minus 3. Okay. All right, so my list that I'm going to test using synthetic division is going to be 1 over 1, 2 over 1. So all the positive and negative versions of these numbers, 1 over 1, 2 over 1. And then 1 over 3, 1 over 3, and 2 over 3. Okay, so those are going to be the four numbers that I choose. Not that I choose, but that I will use in my synthetic division. Okay. X equals 1. I like to try 1 first. Okay. All right. What's my polynomial? Okay, so 3, -5, -8, and -2. 3, 2, 1, 0. Okay, so 3, -5, -8, -2. All right, hoping to get a 0 remainder here. So 3. 3 times 1 is 3. Combined, -5 and 3 is -2. -2 times that outside number 1. -2 times 1 is -2. Combine, I get -10. -10 times 1. And sadly, I do not get a 0 remainder. Okay. All right. So is anyone out there feeling lucky and wants to choose the next number? What? Did I hear you say 1/3? Okay, so let's go ahead and try. Oh, you said -1/3. Okay, so let's go ahead and try -1/3. Okay, so my polynomial is 3, -5, -8, -2. All right, bring down that 3. So 1/3 of 3 is 1, but that's going to be negative. Combine -5 and -1, and we get -6. -1/3 times -1/6 is +2. Combine the -8 and 2, and we get -6. -6 times -1/3 is, again, 2. And, oh my goodness, we get a 0. Not just any 0, but a really happy 0. Okay. All right, so now this x equals -1/3 is a 0. It's also an x-intercept. And this here, these are the coefficients of a degree 2, since we started off with a degree 3 up here. See, degree 3. So these coefficients, 3, -6, -6, are the coefficients of a degree 2, always one less. Okay, so this is 3x squared minus 6x minus 6 equals 0. I notice they're all divisible by 3, so I'm going to go ahead and divide them all by 3. And does this factor? So we can try here, plus, minus, and 2 and 1. And no matter how I put the 2 and the 1, it's not going to work. Okay, so sadly, this is not factorable. Okay, so what I can do is go over here and use quadratic formula. Do you remember the quadratic formula? That song? Okay, so we can go off to the side over here and use the quadratic formula. I'll let you guys do that on your own time, because we actually don't have to here, because if it's not factorable, then you end up with zeros that are either irrational or imaginary. And this question says to find the real zeros. Okay, so Oh, you know what? It says real, not rational. So we do have to use quadratic formula. All right. So let's see. A equals 1, B equals -2, and C equals -2. All right, so let's plug those numbers into the quadratic formula. Negative, B is -2. A is 1, C is -2, all over 2 times 1. So we get +2 plus or minus square root 4 plus 8 all over 2. So that's 2 plus or minus square root of 12 all over 2. That 12 can be broken down, 2 plus or minus. So let me just show you up here. Square root of 12 can be broken down using square root of 4 times square root of 3, right? And square root 4 is 2. Okay. So instead of writing square root 12 here, I am going to use 2 square root 3 over 2. And in the numerator there, I'm going to factor out a 2. And now that 2 is factored out, I can go ahead and cancel it. Okay, and there are my 2 other answers. The first one came up here with the synthetic division. Okay, that's my first answer right over here. X equals -1/3. Scroll down. So our answers are x equals -1/3. And then our other 2 come from right over here. Okay, so x equals 1 plus square root 3. And the other one is x equals 1 minus square root 3. So degree 3, there are my 3 zeros, my 3 real zeros. If we had gotten an imaginary in that square root, then we wouldn't list it here because it says to find the real zeros. Okay. Real zeros, that's any number except for imaginary. Rational zeros are the ones that can be written as a fraction. So square roots, these, if it had said find the rational zeros, we would not include this one or this one. Those are irrational. Square roots are irrational. Okay. Okay, so you can see here that when you have your list of possible zeros, this one's not too bad. It's kind of short, but they can get kind of long, and it could be a pain to test them all. So here are some tricks as far as when to stop. Okay. Okay, so I'm gonna, oops. Okay, so I'm going to talk about something called an upper and lower limit. And this is nice because as you are testing all your numbers, you end up with a set of numbers down below your synthetic division. And so if you get a certain result, then you might have an upper bound, or you might have a lower bound, or you might have neither. Okay, so let's start with this first one. Okay, so let's let P be a polynomial with real coefficients as opposed to imaginary. Okay, so we have this first case. So if you're testing out a number on your list, whatever that number is, okay? X equals B. Okay, I'll just call it B. Okay, and you do your synthetic division, right? You do your synthetic division, you have some numbers there up above, you do your multiplication, your combine, and then you end up with some numbers here, right? I'll just call them A, B, C, D, right? So it turns out that if all of these numbers are non-negative, do I mean positive? Yes, I mean positive. Okay, so if these numbers here turn out to be all positive, then this here, okay, if this is positive, this positive B value is an upper bound. Okay, so you want to pay attention to your results in this row. If you get all positives and the number you're testing out is a positive number, then it's an upper bound. And what that means is you don't have to test any of the other numbers on your list that are larger than this number, because according to this theorem, it says that this B value is an upper bound. Okay, so it means that there won't be any zeros that are larger than this number. Okay, so when you get all positives here, keep that in mind. Okay, now we also have something for a lower bound. Okay, so let's say that you're testing this value, x equals b, right, for your synthetic division. Okay, and this is a negative number. Okay, and again, you get some numbers down below over here. Okay, so here it turns out that if the signs alternate, so if the signs alternate, positive, negative, then this b value over here, then this here is a lower bound, which means you don't have to try any numbers that are smaller than this. Okay, so these are nice because if you find out what your upper bound is, and you have a lower bound, well, now you know. Okay, so your answer needs to be somewhere between this number and this number. Okay, so it kind of narrows down your search on your list. Okay, so let's take a look at some examples here. So not full examples, but let's suppose you were trying this x equals 4, and let's suppose that you get this number here when you do your synthetic division, whatever your polynomial is. Let's suppose you end up with this result. Okay, so we got all positive numbers here, so this x equals 4 is an upper bound. So if 5, 6, 7, 8, 9, 10 are on your list, you don't have to try them. Okay, they're not going to be zeros. Okay, and here, this is what your results would look like if you end up with finding a lower bound. Okay, so let's suppose you were trying x equals -3 in your synthetic division. Okay, and whatever your polynomial is, and then suppose you end up with this result, 5, -2, 0, -3. It alternates signs, positive, negative, positive, negative. Okay, so here, this x equals 3, -3 is a lower bound. So you don't have to try any numbers on your list that are smaller than -3. So if you have like -4, -5, -6, -7 on your list, you don't have to test them. You are not going to get a zero remainder. Okay? All right. And so let's take a look at graphing. Okay, so suppose that I wanted to graph this here. Let's go ahead and graph f of x equals -x cubed minus -2x squared plus 5x plus 6. Okay, so it's all in order. No terms are missing. So my possible p-values here are going to be plus minus 1, 2, 3, and 6. Okay, so plus or minus 1, plus or minus 2, plus minus 3, plus or minus 6. Okay, all the factors of 6. Here, my possible q's are the factors of -1, such as plus or minus 1. Okay, so now my list, my possible list, is going to be all of the p's over +1, all of the p's over -1. Okay, so that's just going to be 1 over 1, which is 1, 2 over 1, which is 2, 3 over 1, which is 3, and 6 over 1, which is 6. Okay, so these are the numbers I'm going to try. All right, so what would you like to test? Who feels lucky? Should we start with 1? That's usually where I always start. What are you guys all yelling at your screen? I'll try to guess what you're yelling. Okay, I hear a lot of you guys yelling, try -1. Okay, so, all right. So I'll skip my tradition of starting with x equals 1, and I'll go with what the audience is saying, which is -1. Okay, and let's see, our polynomial is -1, -2, +5, +6. All right, let's bring down that -1. -1 times -1 is 1. -2 plus 1 is -1. -1 times -1 is 1. 5 plus 1 is 6. 6 times -1 is -6. Oh, look at that, a 0. Imagine. Oops, I'm getting too excited here. Okay, so we get a 0, happy 0. All right, that was a degree 3, yes. So that was a degree 3, so yes, it is. Okay, so this is a degree 2 down here. So let's see if we could factor out this. This is -x squared minus x plus 6. And I'm going to divide everything by negative because I like my leading term to be positive when I try to factor. Okay, so I get x times x, 1 positive, 1 negative. 3, looks like it's going to be 3 and 2. 3 and 2. Yeah. Okay. So x equals 1, -1 is one of my zeros. So it's one of my intercepts. And x equals -3 is also another one. And x equals 2. All right, so I have my x-intercepts. I need my end behavior. Remember that. So let's go back to our original polynomial. Okay, so here, so again, end behavior, we only use the leading term. So as x goes towards positive infinity, f of x goes towards what? Okay, positive infinity will end up with a positive result or a negative result in that first term. We end up with a negative result. Okay, so on the right-hand side, we'll be going down. Okay, and then as x goes towards negative infinity, so plug in a negative number into that first term, and we get negative times negative, which will be positive. So f of x goes towards positive infinity. So this was on the right, and on the left, we'll be going up. Okay. All right, so putting this all together, we have our x-intercepts, we have our end behavior, so I can do my graph. All right, left side should be going up, right side should be going down. I have a 0 at -1. I also have one at -3 and one at +2. Oh, shoot. All right, so my laptop is going slower than my writing. It's probably overheating. Okay, so we have one at -3 and also at +2. None of these are double zeros, so we're going to be up on this end and down on this end. And all of those zeros are cross throughs. Okay, so that's how you're going to be graphing these higher degree polynomials that initially are not factorable. So you have to find maybe that first zero or maybe that second zero using this method. Okay, and then hopefully you'll get a degree 2 that's factorable, and you can find the rest of them. Okay. All right. Factoring. So let's take a look at factoring going backwards. Okay, so we are going to be working backwards. Okay, so work backwards. So what I mean by that is find the zeros first. Okay, so if you know the zeros, like here, right above here, if x equals -3, if you know the zero, then you know the factor it comes from. Just bring that -3 back with the x, so add 3 to both sides. Okay, find the zeros, get the factors. Okay, so for example, you go through your synthetic division, you come up with your zeros, and let's suppose that your zeros are x equals -1, x equals -3, and x equals 2. Okay, if you know all the zeros, you can just work backwards. So let's go ahead and add 1 to both sides, and I get x plus 1. Let me add 3 to both sides, and I get x plus 3. Does that make sense? And let me subtract 2 here, and I get x minus 2. So there are my factors. Okay. All right, so that was quite a bit. So if you have any questions, make sure you email me, message me through the Remind app, okay, or ask me to do a Zoom with you. All right. Okay, so that is it. I will see you guys next time.